Good afternoon, and thank you for joining us. My name is Michelle Holko. I have a PhD in genetics and a master's in scientific clinical investigation, and I'm currently the principal scientific advisor at Computercraft. I want to note that my remarks do not reflect the opinions of my prior employers or organizations. My career has spanned NCBI, DARPA, the White House, Google, and the National Security Commission on Emerging Biotechnology, among others. Across those experiences, from basic research to technology to national security, I've concluded that biological data has become national strategic infrastructure. Before I talk about data and infrastructure, I want to tell you why I became a scientist. My dad grew up poor on the north side of Pittsburgh, but he believed in the power of education, and that belief carried him to mechanical engineering at Penn State and then to law school at George Mason while he worked as a patent examiner at the U.S. Patent and Trademark Office. He was 35 years young when he was diagnosed with stage 3 colon cancer and died when he was only 39 years old. As I learned more over the years, I realized that my dad's cancer was actually an appendiceal cancer, likely traced back to a burst appendix that was treated with antibiotics and sent home instead of surgery because there was no insurance and no money. My dad died young because he grew up poor. When I started grad school, it was right around the time that the Human Genome Papers were being published. Here's a picture of me during that time with my advisor in our lab at the Cleveland Clinic Foundation. Although I didn't work on the Human Genome Project personally, it inspired me and provided an example of what's possible in science and what's possible when the public sector and academia collaborate. It's also personally meaningful to me that Computercraft has supported NCBI's mission since those early years, and that today I have the privilege of contributing to that work. People often talk about the Human Genome Project and the metric of success as how it drove down the cost of genetic sequencing. And it did, for sure. But perhaps the most important legacy, at least the one that I think is the most important, is the creation of a shared scientific infrastructure. The Human Genome Project established the principle that biological data generated through public investment should be made available to everyone. Over the next 2 decades, that vision grew, and what emerged became a new scientific infrastructure, one that today spans dozens of interconnected biological databases, more than 40 million biomedical publications, and billions of biological records. Every dataset deposited once can be reused thousands of times by researchers around the world. Entire careers and countless graduate theses have been built by discovering new biology from publicly available data rather than collecting new experimental data. The Human Genome Project produced one genome, but America's public biological data infrastructure turned one genome into millions of discoveries. Like all great infrastructure, its value has continued to grow long after it was built. And today, AI is dramatically increasing the return on decades of investment in open biological data. Across NCBI, the National Center for Biotechnology Information at NLM, the National Library of Medicine at NIH, more than 3 million researchers every day rely on these resources. GenBank alone contains over 6.5 billion genetic sequences, representing more than 500,000 formally described species. Maintaining this library-quality scientific record at the National Library of Medicine is an enormous undertaking, and it's not a static archive collecting dust. At the moment I captured these numbers from analytics.usa.gov, there were more than 227,000 active users accessing NLM resources within the previous 30 minutes alone. This is living scientific infrastructure that researchers, clinicians, innovators, and students depend on every day. That's what scientific infrastructure looks like. In the AI era, we are only just beginning to find out what's being built using these data. AlphaFold, a protein structure prediction tool developed by Google's DeepMind, is perhaps the most recognizable example. It was built using public biological data. That same infrastructure is already accelerating drug discovery, helping to diagnose rare diseases, enabling genomic surveillance during outbreaks, and providing the foundation on which the next generation of biological AI systems will be built. Biological data is the fuel of biological breakthroughs, and none of it happens without the shared data infrastructure. So what have we learned in the 25 years since the Human Genome Project? Well, we've learned that open biological data creates extraordinary scientific value, But we've also learned something new. Not all data are created equally useful in the age of AI. AI needs data that are machine readable, interoperable, richly described, and accompanied by trustworthy metadata and provenance. If we were building today's biological data infrastructure from scratch, knowing what we know about AI, we would automate much more of the metadata capture and design systems specifically for both humans and machines. Rather than prescribing specific technologies, on this slide are enduring design principles aligned with the National Security Commission on Emerging Biotechnology's vision for a web of biological data. The data should be diverse and representative, so AI models can generalize across populations, environments, and biological systems. They should be high quality and well provenanced, because trustworthy AI depends on trustworthy data. They should be interoperable, using shared standards so data sets can be connected and reused. They should be secure by design, and privacy-producing architectures such as tiered access and bringing algorithms to the data whenever possible should be used. In addition, they should be machine readable by default, with structured metadata and persistent identifiers. As with many transformative technologies, security considerations evolved more slowly than the technology itself. Genomic data security has been slow to catch up. Biology is inherently dual use, which means that the same data and models that can speed up beneficial things like medicines or better crops can also lower the barrier to harm if they're misused. And aggregated biodata becomes a high-value target. But this is not an either-or between innovation and security. The answer is coordinated infrastructure designed with security, access controls, and accountability from the start. The Commission concluded that we had roughly a 3-year window to lead the space or seed it. Since the NSCEB's report was published, we've ceded the lead, the US, but I hope we don't cede the race, the global power competition in biotechnology. No private company has the incentive to build public scientific infrastructure that benefits its competitors. That is exactly why government investment matters. America built this infrastructure. Now it's time to support it into the future. Public investment is literally the substrate that makes private innovation scalable. In terms of recommendations, I've arranged these into 3 pillars. First, invest in biomedical data as national infrastructure. The resources we already lean on, like GenBank, PubMed, ClinVar, GEO, and SRA, and stand up the Web of Biological Data as the bipartisan Web of Biological Data Act proposed by Young, Padilla, Rounds, and Kim. Second, invest in AI-ready data, not just AI models. Standards, metadata, interoperability, and provenance may ultimately matter more for scientific progress than incremental gains in foundation models. In fact, I believe that is very true. The AI-Ready Biodata Standards Act is a vehicle for exactly this. Third, invest in the scientists who will use AI, both from a building perspective and a security standpoint. In my AI enablement work with Computercraft, I've seen that when scientists are supported, they gain confidence, adoption rises, and they build real practical workflows. AI won't replace scientists, but scientists who work effectively with AI will shape the future of discovery. At the same time, the field of biosecurity is rapidly expanding as engineering, biology, and AI reshape the biological ecosystem. Today, relatively few scientists are trained to recognize the security implications of their work. In the future, security thinking will need to become part of scientific practice itself. We need public investment to prepare the next generation of scientists for that future. When I learned later in life that my dad had appendiceal cancer, and not colon cancer, I was also learning that the course of his illness was shaped as much by access to care as it was his own biology. That's why I care about science, and that's why I care about policy, because the true measure of scientific progress isn't what we discover. It's whether the systems we build will give more people the chance to live long, healthy lives. Thank you.